Hello friends, here in this video we will see a problem based on diesel cycle. Here is the question. Whatever is given in this, I'll write that in the form of data along with reading the question. So here the first thing would be to write the data which is given. Now a diesel engine has a compression ratio of 15. So compression ratio is given, that is R suffix C. It is 15, and heat addition at constant pressure takes place at 6% of stroke. So heat addition is at 6% of stroke, that is given. This stroke is nothing but stroke volume. Next, find the air standard efficiency of the engine. See, air standard efficiency for diesel cycle. In case of diesel cycle, our assumption is air is there in more quantity as compared to the fuel, which is diesel. So we have to find out the efficiency of diesel cycle, which is the air standard cycle. And then take gamma for air. Gamma value is 1.4, which is given. And now the type of cycle is, since it is a diesel engine works on diesel cycle. So here is the data for this problem. Now I'll start with the solution to calculate the efficiency of this diesel cycle. Now in the solution part, the first thing would be to draw the PV and TS diagram for this diesel cycle. So I'll write down, it is PV and TS diagram for diesel cycle. Now PV is the pressure volume, TS is temperature entropy. So that diagram is basically a graph. So PV is pressure volume, TS is temperature entropy. Now first I'll write down the processes which are there in diesel cycle. So diesel cycle consists of the following 4 processes, and those 4 processes are: first, process 1 to 2, it is reversible adiabatic or isentropic compression. This is the first process. Next, process 2 to 3 is constant pressure heat addition, because diesel cycle is also called as the constant pressure cycle since the heat is added at constant pressure.
Next,
process 3 to 4 is reversible adiabatic or isentropic expansion. And then process 4th, it is process 4 to 1, which is constant volume heat rejection. So now these 4 are the processes which take place in case of diesel cycle. The first process 1 to 2 is reversible adiabatic or isentropic compression. Now that I'll show it on PV diagram first. The isentropic process on the PV diagram, it is a curve wherein here the process starts at point 1, it ends at point 2, and since this is compression process, we can see that the volume which was V1 initially decreases to V2 finally, and then the pressure rises from P1 to P2. Next, this is the isentropic compression wherein the volume decreases with increase in pressure. The next process 2 to 3 is constant pressure heat addition. So we have to keep the pressure constant and go on adding heat from point 2 to 3. So keeping the pressure constant from 2 to 3, we are adding the heat. So P2 is equal to P3. Then after this, we have process 3 to 4 as reversible adiabatic or isentropic expansion. So this is process 3 to 4, which is reversible adiabatic, or I can say isentropic expansion, wherein the pressure is dropping and the volume goes on increasing. Next, process 4 to 1 is constant volume heat rejection. So during 4 to 1, the heat gets rejected at constant volume. So here we can say that V1 is equal to V4. So it can be seen clearly from the PV diagram that diesel cycle is a process, or it is a cycle in which we have heat addition at constant pressure and heat is rejected at constant volume. Then the compression and expansion processes both are following the curve or law PV raised to gamma is equal to constant. Next, I'll show the diesel cycle on TS diagram. The first process, as it is reversible adiabatic or isentropic compression, so that isentropic compression is shown on TS diagram with a vertical line from point 1 to point 2. Now at this isentropic compression process, the entropy remains constant, that is S1 is equal to S2, and there is increase in temperature from T1 to T2. So this is the isentropic compression process. Next, the second process is constant pressure heat addition. So I'll draw a constant pressure line. Now this line indicates a constant pressure line, and when the heat is added, it will follow this constant pressure line, increasing the temperature T and increasing the entropy S. So process 2 to 3 is constant pressure heat addition. So here the temperature has increased from point 2 up till point 3. Next, process 3 to 4 is reversible adiabatic or isentropic expansion, wherein the entropy remains constant from 3 to 4, that is S3 is equal to S4, but there is drop in temperature from T3 to T4, as we can see here. There is drop in temperature, and this indicates the isentropic expansion. At last, we have constant volume heat rejection. Now, just while drawing the TS diagram, we have to be careful that the constant volume line is more inclined compared to the constant pressure line. So the inclination of constant volume line should look greater. This is the constant volume line, and when the heat is rejected, the process will follow this constant volume line from 4 to 1. Now this is the heat rejection process wherein the temperature decreases from T4 to T1 and entropy decreases from S4 to S1. So 2 to 3 is the heat addition QA, 4 to 1 is heat rejection which is QR, 1 to 2 indicates the work which is done during the compression process, 3 to 4 indicates the work we are getting during the expansion process. So this was the PV and TS diagram of diesel cycle, and now with this understood we can start with the solution to this problem, that is the calculation of diesel cycle efficiency. So now here after the PV and TS diagram I'll go on for the calculation of efficiency of diesel cycle. So the next thing would be to write the formula of efficiency of diesel cycle. So since efficiency of diesel cycle is given by, the formula is efficiency of diesel cycle is equal to 1 minus 1 upon gamma into bracket RC raised to gamma minus 1, next here into bracket rho raised to gamma minus 1 upon rho minus 1. So now I will keep this as equation number 1. That is, I'll go on finding all the values, put them in equation 1 to get the answer of efficiency of diesel cycle. Here, first of all, RC is called as the compression ratio and it is given in the problem as 15. Gamma is 1.4, value of adiabatic index. Now only rho remains. This rho is called as fuel cutoff ratio. So I'll start it in this way, that's after this, therefore rho, which is called as fuel cutoff ratio, and it is equal to volume after fuel addition to the volume before fuel addition. So therefore, what is this? I can explain it with the help of the diesel cycle. Now the ratio is volume after fuel addition. Fuel addition, that is heat addition, starts at point number 2. It gets over at point 3. So at point 3 the volume is V3 and this is the volume after fuel addition. So rho is equal to V3 upon volume before fuel addition. Fuel addition starts at point 2. Here the volume is V2. So V3 by V2 is nothing but the fuel cutoff ratio. Now this fuel cutoff ratio, I will keep it as equation number 2. Next, I'll go on to find this fuel cutoff ratio, because once rho value is known, I can put all the values in equation 1 and get the answer of efficiency of diesel cycle. So I'll look what is given in the problem. They have given something that heat addition is at 6% of stroke volume. It means stroke volume, if I see here in the PV diagram, stroke volume is from, we can say it is V1 minus V2, that is stroke volume is nothing but the distance moved by the piston. So piston can move maximum up to V2 and it can go up to V1. So this is the limit of the piston. So I can say that this distance is nothing but V1 minus V2. So here I'll write down that since stroke volume V suffix S is equal to V1 minus V2, and then in the problem they have mentioned that the heat addition is 6% of the stroke volume. So this heat addition volume, it is only up to the 6% of stroke volume. So I'll say that therefore as the heat is added up to 6% of stroke volume, therefore heat is added from, I can say the heat added duration is from volume V3 to V2, that is this distance V3 minus V2 from this reference 0. The distance V3 minus V2 gives the volume of heat addition. I can show it on the diagram. Now this much is the heat which is added, so it is V3 minus V2, and this is 6% of the total stroke volume, which is V1 minus V2. So now therefore I can write down V3 minus V2 is equal to 6% of stroke volume, which is V suffix S. Therefore V3 minus V2 is equal to 6%. It can be written as 0.06 of stroke volume, which is V1 minus V2. Here as I have mentioned that the stroke volume is V1 minus V2. So 6% of this, that is the heat added. Therefore here if I can see V3 minus V2 is equal to 0.06 into bracket. Now V1 value, as the compression ratio is given as 15, this compression ratio is nothing but the ratio of volume before compression to the volume after compression. The volume before compression is at V1, after compression it goes up to V2, so V1 by V2 is called as compression ratio. Therefore from this I can say that V1 is equal to 15 times of V2. So I'll replace V1 with 15 times of V2 minus V2 into the bracket. I'll write down, since compression ratio RC is V1 by V2 and the value is 15, so from this we are getting V1 is equal to 15 times of V2. Now therefore on calculation I will get this as V3 minus V2 is equal to 0.06, this will become 14 into 15 V2 minus 1 V2, that is 14 V2. Therefore V3 minus V2 will be equal to 0.06 into 14, that is 1.84 V2. Next, therefore V3, I'll send minus V2 onto the other side, so it becomes plus V2. Here this value is 0.84 actually, so when I send minus V2 onto the other side, it will be 0.84 V2 plus V2. So therefore V3 will be 1.84 times of V2. Now I will put this value, therefore put V3 in equation number second. In equation second we are having the fuel cutoff ratio, that is rho is equal to V3 by V2. I'll put the value of V3 here. So therefore rho will become, V3 is 1.84 times of V2 and in the denominator we are having V2. So here I have put the value V3 is equal to 1.84 V2 in equation number second. Now therefore from this I can say that V2 and V2 they get cancelled out, so we are left with rho is equal to 1.84. Now this is the value of rho. After this I'll say that therefore put all values, that is RC compression ratio, rho fuel cutoff ratio and gamma adiabatic index in equation number 1, which gives the efficiency of diesel cycle. So therefore efficiency of diesel cycle will be equal to Now the formula is 1 minus 1 minus 1 upon, it is gamma is 1.4 for air, which is given in the problem, into bracket RC is compression ratio, given as 15, raised to the power gamma minus 1, which is 1.4 minus 1. Next, into bracket, here we are having rho raised to gamma, rho is 1.84, raised to gamma, which is 1.4 minus 1, then divided by rho minus 1, so rho is 1.84 minus 1. So now here I have put all the values, that is of RC, which is compression ratio 15, rho, which is fuel cutoff ratio 1.84, and gamma, which is adiabatic index 1.4. So on calculation, here I'll get this as efficiency of diesel cycle, 1 minus this term is 0.2417 multiplied by this term in the bracket is 1.605. So therefore, for the efficiency of diesel cycle, this will be 1 minus, now this term when I multiply, it comes out to be 0.387. so therefore it is 0.613, and if I multiply this by 100, my answer is 61.3%. So here I am getting this as the final answer, which is the efficiency of the diesel cycle. So if we look into the question, under the given conditions, they were telling us to find the air standard efficiency of the engine, and this air standard efficiency of the engine is nothing but it is efficiency of diesel cycle, because here the engine is diesel engine which is working on diesel cycle. So the efficiency of diesel cycle was found to be 61.3%, and with this we complete the problem.